This video is the start of a full Extension 1 mathematics series where we're going to go through the entire course from the ground up and the way the HSC actually tests it. So we're going to start off with vectors. Now, what is a vector? A vector is something with magnitude and direction. So you can see I have these arrows drawn here where they all have some form of length plus a direction indicated by the arrowhead. Now you can tell that in terms of magnitude, this vector right here is bigger than this vector right here. Now, quick notation. So when we are trying to refer to a vector, there's a couple ways we can do it. One simple way is A with a tilde underneath. Sometimes people write A with the tilde above it. Another way is, let's say this point is A and this point is B. Well, this vector here you could represent as the vector going from point A to point B, with an arrow on top of that head. Now in textbooks, they can also represent vectors by a bold letter. Now, when we want to refer to the length of a vector, we denote it with these symbols that you may have seen before when doing absolute values. This sort of notation indicates the magnitude of some quantity. In this case, it'll be a vector. So we can already tell from this graph that, say, if we call this vector over here B, we already know that the magnitude of AB is clearly bigger than the magnitude of vector B. Just looking at the size. Now that we understand a bit about what a vector is, let's see what happens when we multiply it by a scalar being the opposite of a vector, that is, only having magnitude and no direction. A regular number like 2 is an example of a scalar. So here we have a vector A, which is go right 2 boxes. So there's the direction, right, and there's the magnitude, 2 boxes. So it's a vector. What happens if we times this vector by 2 or half this vector? Does the direction change? Does the magnitude change? Well, every time you times by a positive regular number like a scalar number, only the magnitude changes. So say we have 2A, that would just be go right 4 boxes. Or say we have half A, that would just be go right 1 box. Let's say we have a vector AB. We want to know what the opposite of AB is. The opposite of a vector is a vector with the same magnitude but in the opposite direction. So instead of the arrowhead being here, the start would be there and the arrowhead would be down here where A is. So how do we represent that in mathematics? So we have the vector, we can represent it as A or AB with an arrow above it. To represent it with this notation, you can simply just do minus of A. But with this AB notation, this vector now is actually, instead of going from point A to point B, it's going from point B to point A. So we can actually represent the vector as BA. And so what comes mathematically is that AB actually equals the negative of BA, or vice versa. There's one special type of vector. Say we have a point here called A, and it's the vector that goes from point A to point A. Now you might be thinking, how is this a vector? Well, this is actually called the zero vector. It's the only vector that has no direction and 0 length, commonly referred to as 0 with a tilde underneath. Now let's test your understanding of what a vector is with this simple question. So here we have a vector coming from the origin to this point, which we'll call 1, 2. And let's say we have another vector coming from the point 2, 1 to the point 3, 3. Are these two vectors the same? Now this is something that students might get tripped up on when they first understand what a vector is, but these two vectors both have the exact same magnitude. They both go up 2 boxes and across 1. They have the exact same direction, and that's actually all you need for a vector, just magnitude and direction. So these two vectors are actually identical. So now we've had a look at multiplying vectors by scalars. Let's move on to adding vectors to each other. So here we have a vector A and we have a vector B, and we want to find out what is A plus B. Now remember from the question before, this vector B, I can literally just move it anywhere. So if I can just grab this vector and move it, because where it is doesn't change what vector it is. It's still the same vector. Now the rule is when you're adding, so we have A plus B. So you always go from the head of A, the arrowhead of A, to the tail of B. So you always connect head to tail, right? And the answer is always the vector from the tail of A to the head of B. So this is our answer here. We can call it C. So we can also do this with the other notation. If we call this point O for the origin, call this A for the first vector, and then this sum vector, we can just call it S. Now OS, if we look at OS, that's the vector we're trying to find by adding this vector here and this vector here. You can always write vectors by following different paths. So OS, that's this path, but we can also get to OS by going through this path and then this path. We can get to OS by first going from O to A, and then from A to S. That's just some notation. Now, subtracting vectors is almost identical to adding vectors. So let's say we want to find out what is the vector when we do A minus the vector B. What does this equal? Well, when you subtract a vector, always think about it as adding the negative of a vector, right? We already know how to do this negative vector. We just flip the direction, right? So instead of B pointing that way, negative B will be this way, right? And now when we add these two vectors, all we have to do is connect head to tail. And our final vector is again from the tail of A to the head of B, right? And now this vector here is A minus B. Let's move on to an example question to test your knowledge. So here we have a diagram with points labeled all around this shape. And we also have these points E and F, which represent the midpoint of the edges of the shape. Sometimes questions will give you this, but if they don't, usually it's easiest just to label two vectors. So for example, label this one U, AD is U, and AE is V. This will really help you if the question doesn't tell you to do this. So a sample question could be like, is AE equal to EB and Y? Now AE is this line here, which is V. Now at the start of this example, I said E and F represent the midpoint of these edges. So the length of these two lines are actually the same and they're pointing in the same directions since they're on a straight line. So that means both direction and magnitude are identical. So they are the sW vector. And that's what you would say. You'd say yes, because they have the same direction and magnitude. Now another type of question would be, what is BC in terms of V, W, and U? What I would do first is just trace the path. So we want to get from B to C, what pathways can we take? Well, we can go from B to A. So we can come down this line. Then we could go from A to D. Come across here. And then from here, we can go up to C. So it's just about finding another pathway. Now, what is BA? Well, BA, you can see, is the same direction as V, but opposite. So we know there's going to be a minus sign somewhere. And it's also 2 times the length of V. So this is going to be minus 2V. Now, what's AD? That's just U. And DC, sort of similar reasoning to BA. DC is just 2 times the length of W. Done. Now we are going to do a slightly more difficult question. So this question is, find EF in terms of BC and AD. Now we can use our last part. We already found BC. So first things first, I would always just try and write EF in a path that I can. So we have EF. Now if we look at EF, a pathway we could go is EA, AD, and then DF. So EA is just the negative of V. And then we have AD, which is U. And then DF, which is W. Now, if you look at our answer to the last part, we almost have something similar to BC, but just not quite right. So in BC, we have minus 2v and plus 2w. But in EF, we only have minus v and plus 1w, or just plus w. So first thing I would lean towards is, let's see what happens if we times 2 to both sides of this equation. So we have 2EF equals minus 2V plus 2U plus 2W. And now you can see that 2EF has BC plus an extra U. So BC is minus 2V plus U plus 2W, and EF is minus 2V plus 2U plus 2W. So they only differ by plus U. So we can actually write 2EF as BC plus U. Now U is actually just AD. And so EF is going to equal a half of BC plus AD. Now you can always sanity check, like you can always just look at the diagram and see, does this look roughly right? And it does. If you added BC and AD, you would probably get 2 times the length of EF just by eyeballing it. That's sort of a sanity check you can do. And so this is the answer. Thank you for watching this intro to vectors for Extension 1 Maths in Year 12, HSC, and I'll continue to go through all of the vectors content in Extension 1 in future videos.